Hello, and welcome to Beyond the Cosmics. Before we embark on this incredible journey through the cosmos, share with us where in the world you're watching from. If you're new to the channel, a gentle tap of the subscribe button will mean a lot. It helps more cosmic viewers find their way here. If you're already subscribed, thank you. Your support is what keeps this cosmic journey going. So tonight, as you watch this video, you're hurtling through space at 67,000 miles per hour on a pale blue dot we call Earth. But that's nothing compared to the mind-bending journey we're about to take. Imagine holding a teaspoon. Now imagine that teaspoon filled with something so dense, so impossibly heavy, that it would weigh about 1 billion tons. That's right. A single teaspoon would weigh more than every single human being on Earth combined. And we're not talking about some theoretical material in a lab. This stuff actually exists, floating out there in space right now. Welcome to the utterly insane world of neutron stars. These things are what happens when the universe decides to absolutely destroy a star and compress what's left into something so extreme, so violently powerful, that they make black holes look almost normal. And trust me, by the end of this video, you're going to understand why neutron stars might be the most metal thing in the entire cosmos. But here's what really gets me. We're going to talk about stars that spin hundreds of times per second. Stars with magnetic fields so powerful, they could literally rip the iron out of your blood from thousands of miles away. Stars that cause earthquakes that make anything on Earth look like a gentle massage. And stars that, when they collide, create explosions so bright they outshine entire galaxies. This isn't science fiction. This is just Wednesday in the universe. So buckle up, because we're about to dive into one of the most beautiful and absolutely terrifying phenomena that nature has ever created. The death of a star. To understand neutron stars, we first need to talk about how they're born. And spoiler alert, their birth is incredibly violent. Every star in the universe is engaged in a constant battle. It's fighting against its own gravity, which is always trying to crush it down into nothing. And what's keeping gravity from winning? Nuclear fusion in the star's core. That's right. The star is basically running on a continuous nuclear explosion that pushes outward, balancing the crushing weight, trying to squeeze inward. For most of a star's life, this works out pretty well. Our sun, for example, has been happily fusing hydrogen into helium for about 4.6 billion years, and it's going to keep doing that for another 5 billion or so. It's a nice, stable existence. But here's the thing. Eventually, every star runs out of fuel. For small stars like our sun, running out of fuel is kind of a slow, sad affair. They puff up into red giants, shed their outer layers, and leave behind a white dwarf. It's the stellar equivalent of retiring to Florida. But for massive stars, stars that are at least 8 times more massive than our sun, when they run out of fuel, things get absolutely catastrophic. These massive stars don't just fuse hydrogen. They're so hot and dense that they keep fusing heavier and heavier elements. Hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, and so on. The star becomes like an onion, with layers of different elements fusing at different depths. And at the very center, iron. The star builds up an iron core. Now here's the problem. Iron is basically a dead end. You can't get energy from fusing iron. It actually costs energy to fuse iron into heavier elements. So when the core becomes iron, the nuclear furnace shuts off. The outward pressure disappears, and gravity wins. What happens next is so fast, so violent, that it's hard to even comprehend. The iron core, which might be about the size of Earth and contain more mass than our entire sun, collapses. In about 1 second, It shrinks from something the size of a planet to something about the size of a city. 1 second. From Earth-sized to city-sized. The collapse happens so quickly that the outer layers of the star don't even realize what's going on at first. They're still falling inward, expecting to hit the core. But now the core is tiny and incredibly dense. When those outer layers finally slam into it, they bounce. That bounce creates a shockwave that tears through the entire star, ripping it apart in one of the most energetic events in the universe, a supernova. For a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. It releases more energy in seconds than our sun will produce in its entire 10 billion year lifetime. These explosions are so powerful that they forge all the heavy elements in the universe. Everything heavier than iron. The gold in your jewelry, the uranium in nuclear reactors, the platinum in your catalytic converter. All of it was created in supernova explosions. But we're not here to talk about the explosion. We're here to talk about what's left behind. That collapsed core, that impossibly dense ball of matter that caused the bounce, that's a neutron star, and it's about to get weird. What is a neutron star? So, let's talk about what a neutron star actually is, because the physics here gets absolutely bonkers. Remember how I said the core collapses from Earth-sized to city-sized? Let me be more specific. A typical neutron star is only about 20 kilometers across. That's about 12 miles. You could drive across a neutron star in about 15 minutes at highway speeds, if there was a highway. And if you didn't immediately get crushed into a paste of subatomic particles. But we'll get to that. Here's the really insane part. That 20-kilometer ball contains more mass than our entire sun. Some neutron stars are even more massive, packing up to about twice the sun's mass into that same tiny space. To put this in perspective, if you took our sun and compressed it down to neutron star density, it would be about the size of a large city. If you compressed Earth down to neutron star density, it would be about the size of a marble. Actually, smaller than a marble, more like a small pea. This level of density is so extreme that it breaks everything we think we know about matter. Under normal circumstances, atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus would be like a marble in the center, and the electrons would be tiny specks flying around the outer walls. There's a lot of nothing in between. But in a neutron star, that empty space is gone, completely obliterated. The gravity is so intense that it squeezes atoms together until the electrons are forced into the protons in the nucleus. When an electron and a proton combine, they form a neutron, hence the name neutron star. The entire star becomes a ball of neutrons packed so tightly together that they're basically touching. It's like matter has been compressed to its absolute limit before it would collapse into a black hole. This is why a teaspoon of neutron star material weighs 1 billion tons. You're not scooping up atoms with a lot of empty space. You're scooping up pure nuclear matter, the densest stuff in the universe that isn't a black hole. Actually, here's a fun thought experiment. If you could somehow take a chunk of neutron star material and bring it to Earth, what would happen? Well, first, good luck getting it here because it would weigh billions of tons. But let's say you managed it. The moment you let it go, it would immediately explode with the force of thousands of nuclear bombs because the neutrons are only held together by the immense gravity of the neutron star itself. Without that gravity, the material would violently decompress. It would punch through the Earth like it wasn't even there, probably causing an extinction-level catastrophe. So let's not do that. The surface of a neutron star is equally bizarre. It's thought to be a crystalline crust made of iron nuclei, but iron unlike anything we've ever seen. This iron is under so much pressure that it forms into incredibly strong lattices, making the neutron star's crust harder than diamond. In fact, It might be the strongest material in the entire universe. As you go deeper into the neutron star, things get even stranger. Below the crust, you enter regions where the neutrons form exotic states of matter that we've never observed anywhere else. There might be layers where neutrons arrange themselves into bizarre structures like rods, plates, or even spheres that scientists poetically call nuclear pasta, because these structures supposedly resemble spaghetti, lasagna, and gnocchi. And at the very core, nobody really knows. The pressures are so extreme that our physics breaks down. There might be free quarks swimming around, the fundamental building blocks of neutrons and protons. Or maybe something even stranger. We literally don't know, because we can't recreate these conditions anywhere, and we can't exactly go there to check. But the density is only the beginning of the neutron star story. Because these things don't just sit there being dense. Oh no, they spin, they pulse, they beam, and they do all of it at speeds that seem to violate common sense. Pulsars, cosmic lighthouses. In 1967, a graduate student named Jocelyn Bell Burnell was analyzing radio telescope data when she noticed something weird, really weird. She found a signal that was pulsing with incredible regularity, about once every 1.3 seconds. Tick, 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 like clockwork. The signal was so regular, so precise, that the research team briefly considered whether it might be artificial, like maybe aliens. They even jokingly called the signal LGM1, which stood for Little Green Men 1. But it wasn't aliens. It was something almost as strange. A pulsar. A pulsar is a neutron star that's spinning rapidly and beaming radiation from its magnetic poles. As it spins, these beams sweep across space like a lighthouse. And if Earth happens to be in the path of one of those beams, we see a pulse of radiation every time the beam sweeps past us. Hence the name pulsar. Now, you might be thinking, okay, spinning once every 1.3 seconds, that's pretty fast. And you'd be right. That is fast. But here's the thing. That was actually one of the slower pulsars. Some pulsars spin hundreds of times per second. Let that sink in. An object with more mass than the sun, compressed into a ball the size of a city, spinning hundreds of times per second. The fastest pulsar ever discovered, PSRJ 1748-2446 AD, spins 716 times per second. That's over 700 complete rotations in the time it takes you to say neutron star. At the equator of this pulsar, the surface is moving at about 24% the speed of light, a quarter of the speed of light. If it spun much faster, the centrifugal force would literally tear it apart. But why are neutron stars spinning so fast in the first place? It comes down to something called conservation of angular momentum. The original massive star was rotating, like all stars do. Our sun rotates about once every 27 days. But when the core collapses during the supernova, it's like a figure skater pulling in their arms during a spin. The rotation speeds up dramatically. A star that was leisurely rotating once a month suddenly becomes a neutron star, spinning multiple times per second. And here's the beautiful part. Pulsars are some of the most precise clocks in the universe. Some of them are more accurate than atomic clocks on Earth. They pulse with such regularity that scientists can use them for navigation, like cosmic GPS satellites. There are even proposals to use pulsars to help spacecraft navigate in deep space, since they're more reliable than anything we could build ourselves. But the spinning is only part of what makes pulsars so extreme. Remember how I mentioned magnetic poles? Yeah, we need to talk about those. The magnetic fields of pulsars are absolutely ludicrous. Earth has a magnetic field. It's strong enough to make compass needles point north and create beautiful auroras near the poles. A typical refrigerator magnet has a magnetic field of about 100 Gauss. An MRI machine, which is one of the strongest magnets most people will ever encounter, has a field of about 30,000 Gauss. A typical pulsar? About 1 trillion Gauss. That's with a T, trillion. To put that in perspective, at a distance of 1,000 kilometers, about 600 miles, a pulsar's magnetic field would be strong enough to rip the atoms in your body apart by pulling on the electrons more strongly than they're bound to the nuclei. Your body would essentially disintegrate at the molecular level. Even from the distance of the Moon to Earth, a pulsar's magnetic field could destroy all the data on every credit card, hard drive, and electronic device on the planet. These magnetic fields are so powerful that they distort the quantum vacuum around the star, creating bizarre effects we've never observed anywhere else. They can actually cause space itself to behave differently near the neutron star. And remember how I said pulsars beam radiation from their magnetic poles? This radiation isn't just radio waves. It's a whole spectrum. Radio, visible light, X-rays, gamma rays. Some of the most energetic radiation in the universe is streaming off these spinning cosmic lighthouses. But we're still not at the most extreme type of neutron star. Oh no. Because there's a special class of neutron stars that takes everything we've talked about and cranks it up to 11. They're called Magnetars, and they are absolutely terrifying. Magnetars. When neutron stars go metal, imagine taking a pulsar, which is already one of the most extreme objects in the universe, and giving it a magnetic field that's 1,000 times stronger. Congratulations! You've just imagined a magnetar. Magnetars are neutron stars with magnetic fields of about a quadrillion Gauss. That's 1 quadrillion Gauss. These are the strongest magnetic fields known to exist anywhere in the universe. To give you some sense of scale, within about 1,000 kilometers of a magnetar, the magnetic field is so strong that it would literally restructure the atoms in your body. Your atoms wouldn't just be pulled apart. They'd be stretched into thin needles along the magnetic field lines. Water molecules would become paramagnetic, meaning they'd be strongly attracted to the magnetic field. Your blood, which contains iron, would be ripped from your veins. But you'd never get close enough to experience this because at distances of hundreds of thousands of kilometers, the tidal forces from the neutron star's gravity would already have turned you into spaghetti. Getting killed by gravity would actually be a mercy compared to what the magnetic field would do. From even farther away, thousands of kilometers out, the X-rays being emitted by the magnetar would deliver a lethal dose of radiation in milliseconds. Your body would be cooked from the inside out by high-energy photons. Magnetars are not friendly places. But here's where things get really interesting. Magnetars have what scientists call Starquakes. Remember how I mentioned that neutron stars have a solid crystalline crust? Well, as a magnetar's incredibly powerful magnetic field shifts and adjusts, it can stress that crust until it cracks. And when a crust made of the strongest material in the universe cracks, it's not a subtle event. These starquakes release enormous amounts of energy. In a fraction of a second, a starquake on a magnetar can release more energy than our sun produces in 100,000 years. This energy comes out as a burst of gamma rays and X-rays so powerful that it can be detected from thousands of light years away. In 2004, a magnetar called SGR 1806-20, located about 50,000 light years from Earth, had a starquake. The burst of gamma rays it released was so intense that it actually affected Earth's upper atmosphere. Despite being halfway across the galaxy, it was the largest explosion ever observed from an object outside our solar system. Scientists calculated that if this magnetar had been just 10 light years away, still an enormous distance, the gamma rays would have caused a mass extinction on Earth, destroying our ozone layer and bathing the surface in lethal radiation. And this happens because the crust cracked a few millimeters. The really fascinating thing about magnetars is that we're not entirely sure how they get such powerful magnetic fields in the first place. The leading theory is that they're formed from rapidly rotating massive stars that collapse with just the right conditions to generate an extraordinarily strong dynamo effect, amplifying the magnetic field to absurd levels. It's like they're the universe's equivalent of winning a really dangerous lottery. There are only about 30 known magnetars in our galaxy, though there are probably more we haven't discovered yet. They seem to be relatively young neutron stars, and their intense magnetic fields appear to decay over tens of thousands of years. Eventually, a magnetar might calm down and become a regular pulsar, though calm down is relative when you're talking about an object that could destroy all life on Earth from 10 light-years away. But as extreme as individual neutron stars are, things get even more spectacular when two of them meet. When neutron stars collide, on the 17th of August 2017, something extraordinary happened. For the first time in human history, we detected gravitational waves from two neutron stars colliding, and it changed everything we thought we knew about the universe. Let me set the stage for you. About 130 million years ago, in a galaxy far, far away, two neutron stars were orbiting each other. They'd probably been locked in this deadly dance for millions or billions of years, gradually spiraling closer and closer together. See, when two massive objects orbit each other, they create ripples in the fabric of spacetime itself, gravitational waves. These waves carry energy away from the system, which causes the orbit to slowly decay. The neutron stars get closer and closer, orbiting faster and faster in what's called a death spiral. As they get closer, things accelerate. They start orbiting each other multiple times per second, these city-sized objects whipping around at a significant fraction of the speed of light. The gravitational waves they're producing get stronger and stronger, the frequency increasing like a cosmic chirp, and then they collide. The collision itself is almost impossible to comprehend. We're talking about two objects, each containing more mass than the Sun, each made of the densest matter in the universe, slamming into each other at close to the speed of light. The energy released in that collision is mind-boggling. For context, a supernova, the explosion of a massive star, releases about 1044 joules of energy. The collision of two neutron stars releases roughly the same amount of energy in a matter of seconds. For those few seconds, the collision outshines everything else in the entire galaxy. But it's not just the brightness that's impressive. It's what happens during the collision. When two neutron stars merge, they create what's called a kilonova. Unlike a supernova, which creates heavy elements through the explosive fusion process, a kilonova creates them through something called rapid neutron capture, or the R process. During the collision, huge amounts of neutron-rich material are ejected into space. These neutrons are then captured by atomic nuclei, creating extremely heavy elements: gold, platinum, uranium, all the really heavy stuff on the periodic table. For decades, scientists weren't entirely sure where these elements came from. The collision we detected in 2017 finally gave us the answer: neutron star mergers. The amount of gold produced in that single collision, estimates suggest it was about 200 Earth masses worth of gold. That's not 200 Earth masses of material. That's 200 Earth masses of pure gold. More gold in a few seconds than exists in all the planets, moons, asteroids, and comets in our solar system combined. Every gold ring, every gold tooth filling, every gold Olympic medal, the atoms in that gold were almost certainly created billions of years ago in a neutron star collision somewhere in space, long before our solar system even existed. But the story doesn't end with the collision. What happens after two neutron stars merge depends on the total mass of the system. If the combined mass is below a certain threshold, about 2.5 to 3 times the mass of the Sun, the result is a bigger, more massive neutron star. This hypermassive neutron star might be stable, or it might be spinning so fast that only its rotation keeps it from collapsing further. But if the total mass is too high, gravity finally wins its ultimate victory. The merged object collapses into a black hole. This is actually one of the ways we think stellar mass black holes can form, not just from the direct collapse of a massive star, but from the merger of two neutron stars that together are just too heavy to exist as neutrons anymore. And here's the really cool part. The 2017 detection wasn't just gravitational waves. Telescopes all over the world, observing in every wavelength from radio to gamma rays, turned to look at the same spot in the sky. We saw the kilonova brighten and fade over the course of days and weeks. We detected the gamma ray burst at the moment of collision. We saw the spectral signatures of heavy elements being formed. It was the first time we'd observed a cosmic event using both gravitational waves and electromagnetic radiation. Scientists call this multi-messenger astronomy, and it opened up an entirely new way of studying the universe. Since then, we've detected more neutron star collisions, each one teaching us something new about physics, gravity, and the formation of heavy elements. And every detection is a reminder of just how violent and creative the universe can be. But let's zoom out for a moment and think about what all of this means. The bigger picture. 31 to 0, 35 to 0. Neutron stars are more than just cosmic curiosities. They're fundamental to understanding how the universe works and how we got here. Think about it. The atoms in your body, especially the heavier ones, were probably created in a supernova or a neutron star collision billions of years ago. You are literally made of stardust, forged in some of the most violent events the universe has to offer. The calcium in your bones, the iron in your blood, the gold in any jewelry you might be wearing. All of it came from dying stars and colliding stellar remnants. Neutron stars also represent the laboratory for extreme physics. We can't recreate the conditions inside a neutron star anywhere on Earth. The densities are too high, the gravitational fields too strong, the magnetic fields too intense. So neutron stars are natural laboratories where we can study matter and energy in regimes that are completely impossible to access any other way. They're testing grounds for Einstein's general relativity, pushed to its limits. They help us understand nuclear physics at extremes we could never achieve in a particle accelerator. They might even help us figure out whether there are exotic forms of matter lurking in the cores of the densest objects in the universe. And then there's the sheer beauty of it all. Yes, neutron stars are horrifying. They would kill you in countless creative ways if you got anywhere near them. But they're also beautiful. The precision of pulsars, keeping time better than our best atomic clocks. The spiraling dance of binary neutron stars, creating gravitational waves that we can detect across the universe. The spectacular fireworks of a kilonova, seeding space with the raw materials for future planets, and maybe even future life. There's something poetic about the fact that the universe creates such extreme objects. Stars die in spectacular fashion, but they don't disappear. They leave behind these incredibly dense monuments to physics, taken to its absolute limit. And those monuments continue to shape the universe around them, through their gravity, their radiation, and occasionally, their spectacular collisions. We're also still discovering new things about neutron stars. As our telescopes and detectors get more sensitive, we're finding more pulsars, more magnetars, and observing more collisions. Each new discovery refines our understanding and often raises new questions. For instance, we're still not entirely sure about the equation of state of neutron star matter, basically, how the pressure and density relate to each other inside these objects. Different theoretical models predict slightly different sizes and properties for neutron stars, and by measuring them precisely, we can test these models and learn about nuclear physics in the process. There's also the question of the maximum mass a neutron star can have before it collapses into a black hole. We think it's somewhere around 2 to 2.5 solar masses, but we're not certain. Finding the most massive neutron stars helps us pin down this limit and understand the boundary between neutron stars and black holes. And then there are the mysteries we haven't even thought of yet. Every time we develop a new way to observe the universe, we find surprises. The first pulsar was a surprise. Magnetars were a surprise. The details of neutron star collisions surprised us. What will we discover next? In conclusion, so here's what I want you to take away from all of this. Neutron stars are the universe showing off. They're what happens when nature says, "You think you understand physics? Watch this." They're the densest objects in the universe that aren't black holes. They spin at rates that seem to defy common sense. They have magnetic fields that could destroy you from thousands of miles away. They experience earthquakes that release more energy than our sun will produce in thousands of years. And when they collide, they create explosions so bright they outshine entire galaxies and forge the universe's heaviest elements in the process. They're the remnants of stars that died in the most spectacular way possible, and yet they continue to influence the universe for billions of years after their formation. They're cosmic lighthouses, helping us navigate the structure of space-time itself. They're laboratories for extreme physics, teaching us about matter and energy in conditions we could never replicate on Earth. And perhaps most importantly, they're proof that the universe is far more creative, far more extreme, and far more beautiful than we could ever imagine on our own. The next time you look up at the night sky, remember, somewhere out there, right now, there's a neutron star spinning hundreds of times per second, beaming radiation across the cosmos. There are magnetars with magnetic fields so powerful they warp the fabric of space itself. And somewhere, in some distant galaxy, two neutron stars are slowly spiraling toward each other, bound for a collision that will light up the universe and create elements that might someday become part of a planet or a star, or maybe even something alive. That's the beautifully horrifying power of neutron stars. They destroy, they create, they persist, and they remind us that we live in a universe where the impossible happens every single day. Thanks for watching. If you learned something today, or if your mind is appropriately blown, let me know in the comments. And remember, the universe is stranger than we can imagine. Sometimes, it's stranger than we can imagine. Until next time, keep looking up.